these are some of my favorite math stories. In this episode, Mathematics is Playful. We'll look at the computer game Minesweeper. You can see math in action in a more modern game if you look at my colleague Mike Wesselcouch's work with Minecraft, either on his YouTube channel or in his paper at the address listed. Now, back in the day, I played Minesweeper several times a day. Sometimes it was a nice mental break from work. Sometimes it was fun trying to set a new personal best. Now, my in the day was long enough ago, I probably need to tell you how it's played. There is a grid. This is a small one, which is for beginners, larger as you get better, of spaces, some of which contain a mine and some of which do not. The goal is to identify where all of the mines are. You can left-click to reveal a site, but if that site contains a mine, the grid explodes and you lose the game. You can right-click spots that you think contain mines, and these are safe spots. The 0, 1, 0 on the left of this grid shows that there are 10 mines total. The counter on the right is a timer. You start by left-clicking somewhere on the grid. There's never a mine on your first site. If an entire region is free of mines, it will open up for you. Now, my first click resulted in this. There are no mines in the blank spaces. The numbers tell you how many mines are adjacent to that square. So the one in the third row, far left, tells us that one of the two sites in the fourth row, far left, are mines to avoid. The one in the third row, second column, right next to it, tells us that one of the three adjacent squares is a mine. So we go down or either diagonal. One of those is a mine. The one at the corner tells us that one of the 5 adjacent sites is a mine. So diagonal left, straight down, diagonal right, straight to the right, diagonal up. Our task is to use those 5 clues that are showing to determine where the mines are. And this is where the math comes into play. What can we logically deduce? In the fourth row, one of the first 2 sites has a mine, and one of the first 3 sites has a mine. Logically, then, the third slot does not have a mine. When we added that site, the mine count did not go up, so it's safe to left-click on that spot. Similarly, the third row, fourth column does not have a mine. Starting at the top, one of the first 2 sites is a mine, and one of the first 3 sites is a mine. The third site cannot have a mine. If we left-click on both of those spots, the grid opens up a lot more, and we now have this. The first 2 sites at the top must contain mines, so we can right-click on them. Notice that the mine sites are marked with flags, and the counter on the left now shows 8. After marking 2 mine sites, we have 8 more to go, and we continue from there, try to clear out the whole grid. There are several shortcuts to make the game easier and faster. In this case, a mathematician would use the word theorem instead of shortcut. A theorem is a statement that can be logically deduced to be true from other accepted truths. Theorems are often in the form of an if-then, so that whenever the if part is true, the then part logically follows. Theorems are the building blocks of theoretical mathematics, constructing a fortress of incontrovertible facts. Now that is all starting to sound rather grand and perhaps frightening. To lighten the mood, note that we've already proven a couple of theorems. For example, if you have a 1-1-1 pattern with no undetermined sites to the left, then that third site does not contain a mine. We use that twice above. A more complicated rule, a theorem, is helpful in the following situation. We'll describe this as a 1-2-1 pattern, looking at the left part of this partial grid. The rule is that, guaranteed, there are mines in the first and third squares. There are a couple of ways to prove this. One way is called a direct proof. The initial 1 says that one of the first 2 sites has a mine, and the 2 says that 2 of the first 3 sites have mines. When we add the third site, the mine count goes up, so there must be a mine there. So we have don't know, mine. Now, the one above the M site says that there is only one mine in sites 2, 3, and 4, so we already have a mine in site 3, that's it. There cannot be a mine in site 2. So now we know something, and then no mine and a mine. And then since one of the first 2 sites has a mine, it must be in the first site, giving us mine, no mine, mine. Proof number 2 is called indirect, and it looks like trial and error, but we'll focus on the error part and produce what is called a proof by contradiction. The first site either has a mine or it doesn't. Suppose it doesn't. So we've got a blank, and then we don't know. Since one of the first 2 sites has a mine, it then must be in the second site. So we have a blank and then a mine, and we don't know the third. Then the 2 above the M tells us that there are 2 mines in the first 3 sites. We only have 1, we need 1 more, so it must be blank, mine, mine. But this can't be right because there's a 1 above that second M, so there's only 1 mine adjacent to that third site. Since our guess of no mine in site 1 leads to a falsehood, it can't be true. This means that the first site does have a mine, and if you follow through the number of mines, you've got mine, blank, mine. Which proof do you like better? I think the first one is clever, while the second one is more mechanical. What's nice about mechanical is that it can work in situations that are too complicated for me to be clever. In this example, there were no undetermined sites to the left of the 1, 2, 1. Does the mine, blank, mine conclusion still hold if there are sites to the left? For example, something, something, 1, 2, 1, and then some more stuff pattern. Pick your favorite proof from above and verify that it works in this case also. Now, a rule like this is great. You can look through a large grid. If you see a 1, 2, 1 anywhere, there's a guarantee that there are mines next to the 1s and not next to the 2. Knowing this pattern simplified Minesweeper tremendously for me, giving me some automatic conclusions that I didn't need to think hard about. There are, of course, many other patterns. Another one that shows up frequently is 1, 2, 2, 1. Now the solution is blank, mine, mine, blank. The mines are in the middle. The proof can either be 1 direct or 2 indirect, as above. Direct and indirect are basic types of proof techniques that you learn in an Introduction to Proofs course, usually taken by math or computer science majors, but invaluable for prospective law students and others as well. Be careful with your conclusions. What does the pattern 1, 1, 1 imply? First, assume that there are no cells to the left or right that are undetermined. Then you can use a direct, clever proof to show that the mine must be in the middle, as in blank, mine, blank. But this logic does not work if there are other undetermined sites to the left or the right. Can you see the flaw? There are 2 ways for the mine count to stay the same as you move from left to right, for example. One is no mine in the next cell moving left to right, but it could also be that when we move to the right, our window loses a mine on the left and gains 1 on the right. For example, the 1, 1, 1 could be mine, blank, blank, mine if there are further items to the left. So be careful about your assumptions. I'm often so clever with my logic that I make mistakes. Here's some more patterns you can try. In doing so, do you feel like you're doing math? Well, if you're using logic and trying to decide what must be true versus what might be true, whether there are numbers involved or not, you are doing mathematics. And for me, this is almost as much fun as playing the game itself.